As Stephen Strogatz once said, since the time of Newton, humanity has come to realize that the laws of physics are always expressed in the language of differential equations. But this mathematical language extends far beyond physics. It shapes the way we describe countless natural and human-made systems. Learning to speak it, it gives you a new way to see the world around you. In this lesson, I'd like to take you on a guided tour through this fascinating subject. My goal is to give you a big picture understanding of what differential equations are all about, while also exploring some detailed examples along the way. I'll assume you're already familiar with the basics of calculus, things like derivatives and integrals. Later on, we'll need a little linear algebra too, but not much more than that. Differential equations appear whenever it's easier to describe how something changes than to describe its absolute state. For example, it's often simpler to describe why a population is growing or shrinking than to explain why it currently has a specific size. The same logic applies to emotions. It might be easier to describe why your love for someone is increasing or fading than to pinpoint why it's at a particular level right now. In physics, particularly in Newtonian mechanics, motion is usually described in terms of forces, and forces determine acceleration, which itself represents change. Differential equations come in two main forms: ordinary differential equations, ODEs, and partial differential equations, PDEs. ODEs deal with functions that depend on a single variable, often time. PDEs, on the other hand, describe functions of multiple variables like time and space. For now, we'll focus on ODEs because they're the simplest to visualize. PDEs, like those used to describe how temperature spreads through a metal rod or how air flows over a wing, will come later. Even though time is the most common independent variable, it doesn't have to be. The main idea is that we're describing how something changes in response to something else, and time just happens to be the easiest case to picture. Physics gives us a great sandbox to explore these ideas, full of simple examples to start with and endless layers of complexity as we go deeper. Let's warm up with something familiar: the motion of an object thrown into the air. Near Earth's surface, gravity causes objects to accelerate downward at 9.8 meters per second squared. That means that every second, the downward component of an object's velocity increases by 9.8 meters per second. We call this value g, the acceleration due to gravity. This is already a differential equation in disguise. If we let yt represent the object's height as a function of time, then its first derivative y dot y, read y dot, gives its vertical velocity, and its second derivative y dot y double dot, gives its vertical acceleration. Gravity tells us that y equals g d dot y equals minus g, a beautifully simple differential equation. To solve it, we can integrate, that is, work backward from the rate of change to the quantity itself. Integrating once gives velocity. Yv equals gt plus y0 y minus gt plus v0 y g equals 0, where v0 is the initial velocity. Integrating again gives position. Y equals 12 g2 t plus y equals v0 t plus y equals 21 gt2 y1, where y0 y0 is the initial height. And just like that, we've solved our first differential equation. We've determined how the object's position changes over time, starting from a simple rule about its acceleration. But this was a very simple case because gravity was constant. Things get much more interesting when the forces depend on position, like in the motion of planets or moons, where gravity changes depending on how far apart the objects are. Things become more intriguing when the forces acting on an object depend on its position. Consider the motion of planets, stars, and moons. In this case, the force of gravity is no longer constant. It depends on the distance between the two bodies. According to Newton's law of universal gravitation, the attractive force between two masses is directed along the line connecting them, with a strength inversely proportional to the square of their distance. Mathematically, this means that acceleration isn't just a fixed number like 9.8. It's a function that changes depending on where the object is. Once again, the rate of change of position gives velocity, and the rate of change of velocity gives acceleration. But now acceleration itself depends on position. So we get a sort of dance between two quantities, position and velocity, each influencing how the other evolves over time. It's like watching two celestial bodies orbiting one another, each one's motion shaping the other's future path. This captures the essence of differential equations. We're often trying to find a function whose derivatives, the rates at which it changes, are defined in terms of the function itself. In physics, most of the equations you'll meet are second-order differential equations, meaning the highest derivative involved is the second derivative. That's because most physical laws, like Newton's F equals MAF equals MAF equals ma, link acceleration, a second derivative of position, to some function of position and velocity. If an equation involves third or fourth derivatives, we call it a higher-order differential equation. These tend to describe systems with more intricate behaviors and dependencies, like systems with memory, where the present depends on the past in a more complex way. When you really stop to think about it, studying one of these equations feels like trying to solve an infinite jigsaw puzzle. You're not just solving for one number, you're solving for an entire function, meaning infinitely many numbers, one for each point in time. But those numbers are connected in a very specific way. Each must fit perfectly with its rate of change, and the rate of change of that rate of change, and so on. To get a more intuitive feel for how this all works, let's look at a simple but rich physical system, a pendulum. Suppose you have a pendulum swinging back and forth. We want to describe how the angle, usually denoted theta, 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 changes over time. In introductory physics, you might have learned that a pendulum exhibits simple harmonic motion, meaning it swings like a sine wave with a period. T equals 2 pi LGT equals 2 pi sky, T equals 2 pi GL, where LLL is the pendulum's length and GG is the acceleration due to gravity. However, that neat formula isn't quite the full truth. It's an approximation that only holds when the angle theta 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 is small. In reality, if you pull the pendulum farther back, its period gets longer than that prediction, and the motion stops looking like a perfect sine wave. Let's see what's really going on. We'll measure the position of the pendulum's bob, the weight, as a distance xxx along the circular arc of its swing. Since the arc length is related to the angle by x equal L theta x equals L theta x equals L theta, we can express everything in terms of theta theta theta. Gravity pulls straight down with acceleration ggg, but because the pendulum is constrained to move along its circular path, we only care about the component of gravity along that path. A bit of geometry shows that this tangential component equals g and theta times theta minus sine theta. The minus sign just means the force always acts opposite to the displacement. It pulls the pendulum back toward the center. Using Newton's second law, A equals dux dt2a equals lafrac d2x dt2a d equal d2 d2x, and substituting x equal L theta x equals L theta, we get L theta equal minus tenth L theta minus g sine. L theta equivalently, or equivalent g d nit theta spot nana L theta. That's the differential equation of motion for a simple pendulum. In the real world, the pendulum gradually slows down due to air resistance and friction at the pivot. To model that, we add a damping term proportional to velocity. Theta equal minus g theta minus mi da theta minus frac gl minus mu theta mathematical 4, where mu is a positive constant that represents how much energy is lost each swing. Now we have a nonlinear second-order differential equation. Nonlinear because of that sine term, it makes the problem much harder to solve analytically. At first glance, you might assume that the sign in the equation explains why the pendulum moves like a sine wave. Ironically, the opposite is true. It's because the sine function appears inside the equation that the motion isn't perfectly sinusoidal. If you simplify the equation by assuming small angles, sin theta, theta theta, approx theta theta pi theta, then you get theta equal minus gl theta equals minus frac gl theta theta theta, and that does yield a perfect sine wave. But as soon as you include the true sine term, things get messy and much more interesting. This example shows one of the central truths about differential equations. They're really hard to solve exactly. Even if you remove damping, mu equals 0, mi equals 0, finding a precise solution for theta t requires using advanced mathematical functions, elliptic integrals and inverse integrals you've probably never heard of. Add damping back in, and there's no known closed-form solution at all. So instead of solving it directly, we often look for ways to understand and visualize what the solutions mean, even without explicit formulas. Now that we've set up our pendulum equation, let's step back and ask, how can we visualize what this equation means? At first, you might be tempted to imagine a graph of theta theta, the pendulum's angle, versus time tt. That's fine, but it only gives you one specific motion, one possible path for a given starting point. What if we want to understand all possible motions of the pendulum at once for different initial angles and speeds? To do that, we need a new kind of picture, a state space diagram. The state of a system means the information you need to describe it completely at a given moment. For the pendulum, the state is determined by two numbers, the angle theta theta and the angular velocity theta theta. Those two numbers are enough to predict the pendulum's entire future motion, assuming we know the equation of motion. If we imagine each possible combination of theta as a point on a two-dimensional plane, then every possible state of the pendulum corresponds to one point in that plane. This plane, the collection of all possible states, is called the state space, or sometimes the phase space. As time moves forward, the pendulum's angle and angular velocity change, meaning the point representing its state moves around in this space. The path that the point traces out is called a trajectory. Let's imagine starting from some initial condition, say theta equals 3 theta equal frac pi, 3 equal 3 pi, 60 degrees, and theta equals 0 theta equals 0. At that moment, the pendulum is displaced but not moving. The equation tells us the acceleration, so we can compute how theta toward theta changes next. Then we can see how theta changes after that, and so on. Plotting all these updates gives a curve that spirals inward toward the origin since the pendulum loses energy due to friction. That spiral represents the pendulum slowing down and eventually stopping. The origin equals 0, theta equals 0, dot theta equals 0, equals 0, is the point where it hangs straight down, motionless. At first, this kind of diagram might feel abstract. It doesn't show the physical pendulum swinging, just a point moving around a plane. But the beauty is that this single diagram shows every possible motion the pendulum could have, not just one. For example, if the pendulum starts with a large velocity, the point in state space might loop around several times before spiraling inward, corresponding to the pendulum spinning all the way around its pivot before slowing down. If there were no friction, mu equals 0, mu equals 0, the trajectories would be perfect closed loops, representing perpetual oscillation. And if we increase the damping coefficient mu, the spirals tighten, showing faster energy loss. This visualization makes complex dynamics easier to see. Even if you didn't know it was a pendulum, you could tell from the diagram that increasing momentum causes the system to settle down faster. That's one of the most powerful things about phase diagrams. They let us see stability and change directly without solving the equations. Let's take this a step further. In state space, we can think of each point, theta, dot theta, theta4, as having its own velocity vector, a little arrow showing which direction the system will move from that state. That's what our differential equation actually gives us. If we define a state vector x quadrant theta math b theta, x equals a theptor, then the equation describes how x math bfxx changes over time. X equaled ffx dot f math x equal ffx. The function fff encodes the rules of motion. It tells us for any current state what the next step looks like. When we draw these arrows everywhere in the plane, we get a vector field, a map of how the system evolves. Each trajectory line you see in the diagram follows these arrows perfectly. At every moment, the point's velocity matches the arrow at that location. This idea, that a differential equation defines a vector field, is incredibly general. It applies to any system of ordinary differential equations, not just pendulums. The only difference is that real systems often have many more dimensions. For example, imagine the famous three-body problem in physics, predicting the motion of three objects moving under mutual gravity. Each body has 3 coordinates for position and 3 for momentum. That's 6 per body, or 18 variables total. So the state space for this system isn't a simple plane. It's an 18-dimensional space. You can't visualize it directly, but mathematically it works just the same. The system's state is one point moving around in that enormous 18-dimensional space, guided by the rules of the differential equations. Physicists call this kind of state space a phase space, especially when the axes represent position and momentum. For the pendulum, if we replace theta angular velocity, with angular momentum, it would fit that definition exactly. Phase space isn't just a pretty visualization, it's one of the most powerful ideas in modern science. It lets us study not just one initial condition, but an entire family of possible ones, all at once. When you look at the collection of all trajectories in this space, it often resembles a flowing fluid. We call this the phase flow. It's like a current showing how states evolve over time. One of the key insights we can get from phase flow is the concept of stability. A fixed point is a state that never changes, where all derivatives are zero. For our pendulum, there are two fixed points. One, the stable one at the bottom, theta equals 0, theta equals theta equals 0, dot theta equals 0, thap equals 0, theta equals 0, where the pendulum hangs straight down. Two, the unstable one at the top, theta equals theta pi, 0 equals pi, that equals 0, where it's perfectly balanced upside down. You can imagine that if you slightly nudge the pendulum from the top position, it will fall. The system moves away from that fixed point. But near the bottom position, small nudges die out. The system moves toward the fixed point. Mathematically, stability is about whether small perturbations grow or shrink over time. Later, we'll see how to determine stability directly from the differential equations by analyzing how the flow behaves near these points. Up to this point, we've used differential equations to describe motion, falling objects, orbiting planets, and swinging pendulums. But one of the most amazing things about these equations is how universal they are. They don't just describe balls and planets, they can model love, economics, ecosystems, and even social behavior. The same mathematics that explains why a pendulum swings can also capture the push and pull of human emotions. Let's borrow an example from mathematician Stephen Strogatz, who once wrote a playful New York Times column about the mathematics of love. Imagine you've been flirting with someone, but your feelings don't always align. You notice that your affection increases when they seem interested in you, but decreases when they act distant. Meanwhile, this person has the opposite pattern. They're drawn to you when you seem cool and uninterested, but pull away as soon as you show too much affection. We could actually describe this back and forth using a pair of differential equations, one for your feelings and one for theirs. The rate of change of your affection depends on how they feel about you, and vice versa. The result is an endless cycle of attraction and repulsion, mathematically, a kind of oscillation. In fact, if you were to plot this on a phase diagram, it would look a lot like the center region of the pendulum diagram we just studied, a smooth looping pattern of motion back and forth. It's literally a pendulum of the heart. And if you add emotional damping, say your partner slows their reactions when they feel too vulnerable, the cycles spiral inward. Over time, both people's emotions level off toward mutual indifference, a stable equilibrium of emotional neutrality. Romantic, isn't it? This may sound whimsical, but it shows something profound. Systems that look totally different, a physical pendulum and a pair of lovers, can follow the same mathematical structure. Even though the equations themselves differ, one uses a sign term, the other might not, the relationships between the variables are similar. That means we can transfer insights from physics to psychology, from mechanics to economics, and so on. In mathematics, it's not what the variables mean that matters, it's how they interact. So far, we've seen that solving differential equations exactly can be very difficult, often impossible. But even when we can't find a nice, closed-form solution, we can still approximate or simulate what the system does. One common approach is numerical integration. Instead of trying to find an explicit formula for theta of t, theta t, we approximate its value step by step. Imagine you're standing in phase space at some point representing the pendulum's current state. The differential equation gives you a vector, a small arrow showing the direction of motion. You take a tiny step in that direction, say for a small time interval, delta t. Then you recalculate the vector at your new position and take another step. By repeating this over and over, you trace out the pendulum's trajectory through time. If delta t is too large, the approximation will be crude. The path will look jagged and unrealistic. But as you make delta t smaller, the result becomes more accurate. With computers, performing thousands or millions of such steps is easy. This process is called solving a differential equation numerically. It's the foundation of most modern science and engineering, from weather forecasting to spacecraft navigation to animation physics. But even numerical solutions have their limits. In the 20th century, scientists discovered that for certain systems, even the tiniest difference in initial conditions, like a change of one part in a million, can lead to completely different outcomes over time. This phenomenon is called chaos. Take the three-body problem, for instance, predicting how three celestial bodies move under gravity. We know the rules perfectly well, and yet even with exact equations and perfect computers, tiny measurement errors can grow exponentially, making long-term prediction impossible. In chaotic systems, the equations are deterministic, meaning they follow fixed rules, but unpredictable in practice. A butterfly flapping its wings in one place can change the weather halfway around the world. This is what we call sensitivity to initial conditions, and it's at the heart of chaos theory. At first glance, that might sound discouraging, as if the universe were taunting us with riddles we can't solve. But there's something reassuring about it too. The complexity we see in the world, in weather, in biology, in human life, doesn't come from randomness or from flaws in our models. It comes from the mathematics itself, from the deep structure of differential equations. In a way, that's comforting. The world's unpredictability isn't chaos without reason, it's chaos with rules. Part 7, Closing Thoughts. The Power of Mathematical Language. So let's circle back to that quote from Stephen Strogatz. Since Newton, mankind has come to realize that the laws of physics are always expressed in the language of differential equations. It's not just physics. Differential equations are the language of change, of how systems evolve, interact, and adapt. Whether you're studying a falling apple, a swinging pendulum, or the dynamics of love and chaos, the same language describes them all. Learning to speak this language doesn't just help you solve problems, it changes how you see the world. You begin to notice that behind every motion, every pattern, every cycle, there's a story written in derivatives and integrals. And sometimes, even when those stories can't be solved exactly, they can still be understood, visualized, and appreciated for their beauty.